Welcome to Dr. Jimmy's Applied Calculus. In section 1.3, we look at equations of again, but in this case, two variables. There's an example, x squared plus 2x plus 4y squared plus 4y equals 2. We have two variables, x and y. But still, an equation. What's the solution? It's a substitution for the variables, and we end up with a true statement from the equation. So different substitutions might give true values, others false. Now we might try to substitute two variables at a time and see, check. Do we get a solution? Don't we get a solution? So there's one way that we might try to find solutions. We use substitution. And start by just substituting for one variable. So if we took x equals minus 1, then the equation would take the form minus 1 squared plus 2 times minus 1 plus 4y squared plus 4y equals 2. If we combined the constants, we could write this as 4y squared plus 4y minus 3 is equal to 0. But we looked at solving any quadratic, so we could use the quadratic formula, we could factor, and in either case we would find that there are two solutions, 1/2 and minus 3/2. So we have pairs x and y, and so we look at those as ordered pairs, putting the x coordinate first. In this case I substituted x equal minus 1, and I found that 1/2 was the solution for y, but I also found minus 1 for x, and the value minus 3/2 also gives a solution. So it's a convenient way to write the solution pairs, x and y, as ordered pairs. Here I found 2. We could continue substituting x's or y's and trying to solve. Said this is one way we could try to find them. Sometimes substitution, we can't solve the equation. In this case I could. It was a quadratic. Now if we take those solution values, minus 1, 1/2, and the other one minus 1, minus 3/2, we can plot those points on a graph. So we have minus 1 for the x of one of the points, and then plus for the y, so we take the corner of a rectangle determined by minus 1/1/2. And that's our point, minus 1/1/2. We could do the same thing with minus 1 and minus 3/2, so we get another point. So there are 2 points in the solution. So we could continue to find points. In this case, if you noticed, we can substitute many values of x and generate values of y. So actually, we could find infinitely many solutions, each one representing a point on a graph. So we could graph the entire set of solutions. That particular set, in this case, if we graph them all, would come together and form a curve. So, usually with a equation in 2 variables, we end up with some curve as the set of solution points. And here I've sketched in somewhat, if we graphed enough points, what the kind of curve we would see. Now, let's look at a more specific setting of linear equations. So those would be first degree polynomial equations. So in a first degree equation, we can have a first degree x to the first, but 2 variables, so we could also have y to the first terms, but we could also have coefficients, so maybe 2 and minus 5. But then there could also be constants. So this would be a typical first degree or linear equation. X to the first, y to the first, and constants. For these, the graph is a straight line. So at some point I got put into the names of these linear equations. So a line determined by 2 points, so let's find 2 points. So just as I mentioned in general, we might try a substitution for one variable. I like to try zeros. So if I substitute x equals 0, the equation becomes 2 times 0 minus 5y equals 10. If I solve for y, I get minus 2. So I have a point, x equals 0, y is minus 2. If I substitute y equals 0, I have 2x minus 5 times 0 equals 10. I have x equals 5. But you can substitute different values for x and y and then solve for the other. Here I've done it. And found 0 minus 2, and then this second point, which is 5 and 0 paired. So if we plotted these points, we have a point here at 5, 0. We also had the point 0, minus 2. In this case, it's a straight line through those 2 points. And we have a graph. Now, if we look at a graph of a line, then the angle, no matter where we move along this line, the angle of elevation is always the same. So this kind of a straight line curve, well, actually it doesn't curve. This remains constant elevation. Now we would like to get an idea of how that elevation works. So if we looked at any 2 points on this line, we could construct a triangle. So a nice right triangle. And so no matter, we could construct it in many places, different sizes. But all of these triangles are what are said to be similar triangles because the angle of elevation relatively is always the same. So these triangles have always the same angles. The sides, though, maybe have different lengths. But if we look at the sides, if we have similar triangles, then the ratio of the two sides in any of these triangles would be constant. So as I put here, if you think of left and right as the run and up and down as the rise, we're looking at rise over run. And so we call that ratio the slope. Also use a little letter M. Okay. For the slope. So rise over run in this picture will remain the same all along the line. So let's look at the line. Let's take two of these points. Look at the triangle. Let's see. So 2 points. Generically for the moment, we'll have points x, y, but the subscript 1 and 2. So 2 different points. If we look at the rise and run in terms of the points, if we move along horizontally on the triangle, that side of the triangle is how far we move in the x direction from x1 to x2, or what we call the change at x, and use the symbol delta x. So it's the difference between the x coordinate values. The other side, what we had called the rise, is a change in the y's. So where we end up minus where we started. So the slope m is the change in y over the change in x, or in terms of the coordinates, difference in the coordinates of the y divided by difference in the coordinates of the x. So, for example, if we have points on a line of minus 2, 3, and the other point was 5, 7, then the slope of a line that passed through those 2 points would be 7 minus 3, so the change in the y, second coordinate, over 5 minus a minus 2 if we look at the x coordinates. And so we get a slope of 4/3. So if we think about that, if we start at a point, we would move in a relative fashion 4 units. Oops. For every 3 units of x up 4. So that ratio, and so that would generate a picture of the line. So always 4/3. So if we go back and look at an equation like 2x minus 5y equals 10, then there's a way to look at this slope in that form. If you take the coefficient of x divide by the coefficient of y, and then change the sign. So minus coefficient of x over coefficient of y in this example would be minus 2 over minus 5. So the slope should be 2 to 5. Again, notice if I start at a point, and if I use the ratio up 2 for every 5 over, I get another point. And an equation, a picture of the line. So we see a picture in this case of the line going up, or as we move across, it increases in height. So we get increasing height. In that case, we would have this triangular picture of 2 to 5 being positive to cause that. But if we look at a line like 3x plus 4y, and we compute the slope, minus coefficient of x over y, minus 3/4, then we would see, if we start at one point on the line, for every 4 units, we would have to then move negative 3 units in that ratio. So it has to be 4 to minus 3. And so we get decreasing height. When the slope is negative. So decreasing line, angle, negative slope, going up, positive slope. Now when we look at lines, we have what you might call the standard or general form. Such as 3x plus 4y equals 12. That same line, we could take the equation, solve for y. In this case, y is equal to minus 3 over 4x plus 3. So a different form of the same line. So in this form we have slope and intercept. So you could find the slope by solving for y and look at the coefficient of x. One other useful form of an equation of a line is if you have a point and the slope. Then you could write down the equation y minus the coordinate of the point is equal to m, and x minus coordinate of the line. For example, if you had a point on the line that was 2, 6 and a slope of 1/2, if you get the equation, y minus 6 is 1/2 x minus 2. Some more examples. Could we find an equation for a line containing 2 points, 2, 4, and minus 3, 6. So the first thing, we could go back and find the slope as a change from 4 to 6 in the y, and minus 3 to 2 in the x, and end up with a slope of minus 2/5. Now we have a choice of 2 points, but we could use, say, the point 2, 4. So y minus the 4 is minus 2/5 x minus the other coordinate of the point, which is 2. What about a slope? Of 3 and y-intercept of 7. So then it would be y equal 3x plus 7. And for any graph, we could always look at the intercept. So if we took 3x plus 5y equals 7, we could compute intercepts. So that's when one variable is 0. For instance, when x is 0, 3 times 0 plus 5 times y is equal to 7. Y is equal to 7/5. Okay, so we get a y-intercept. We could take y equals 0, get 3x plus 5 times 0 equals 7, and get x equals 7/3. So we get the x-intercept. So we can work on slopes, points on a line, different types, but we could also look at the intercepts as 2 of the points. Now, sometimes we have an equation such as y equals 3. It looks like an equation in one variable. But if it's in a setting of 2 variables, it could mean that the coefficient of the other variable is actually 0. So we could be referencing a 2 variable situation even though the one isn't written. So we could look for points. But in this case, x, it doesn't matter which x I substitute, such as minus 1. Y is 3. Or I could substitute x equal 2. Y is still 3. And so for every point, the y value is 3. So we see a straight line of height 3 always. And so the slope is 0. It doesn't go up or down. No rise for any run. vertical lines. So if I have something like x equal 2, and I'm supposed to be talking about ordered pairs x and y, the y is unspecified, so I could get points like 2 minus 1, 2, 2. So any point where the first variable is 2, I can substitute any y, minus 1 in this case, and 2. And so a vertical line, so all the x values are 2, and I move along. But now I can't assign a slope to this vertical line, so because I have no run, so I can't divide. You might say at this time that the slope is undefined, or no defined slope, or no slope. We'll revisit that a little later, but as a real number we can't assign a slope to such lines. So, equations, ordered pairs are the solutions. Now, let's look at the word relationship. So if we take a somewhat non-mathematical setting, maybe, we might have a list of fathers and a list of daughters. So we got to set up this relationship. Who is the daughter of the father? And so Jan might be the daughter of Al. Irene is a daughter of Cam, but also maybe Connie. We look at John. So we can begin to set up these pairings. So if you think of any relationship, it's just a set of pairings. So you could look at every relationship as just ordered pairs. So in the one above, I would have Al associated with Jan. That's an ordered pair in that set. So a relationship, we're very familiar with all kinds of relationships, but they're all just pairings. So a set of ordered pairs. So, mathematically, that's the definition. A relationship is just any set of ordered pairs. So, if we wrote down 2x minus 5y equals 10, that's a relationship. It's a set of solutions which are ordered pairs x, y. So we could look at a graph of the relationship since they're numbers. Probably wouldn't look at a graph in the case of the daughter of relationship, but it's still a set of ordered pairs. So if we looked at the daughter of relationship, we might also consider the father of relationship. And we're looking at the same sets, but in reverse order. So in the daughter of, we have Al. It related to Jan because Jan is the daughter of Al. In the other case, Al is the father of Jan. So we can look at those relationships in two ways, but the pairs are different. It's a little different pairing. If we looked back at that, we had Cam had daughters, Irene and Connie. But if we look at in the reverse or inverse situation, then we would have Irene paired off with the father Cam and Connie paired off with father Cam. So sometimes it's useful to look at a relationship one way and then to come back and look at the relationship in the reverse order. But it's a different relationship because you don't get the same ordering. So we can also take a relationship like 3x plus 5y equals 15. We could look for the inverse relationship. Which would be, write the ordered pairs backwards. Or exchange the first and second coordinates. So instead of 3x, it's 3y, and 5 instead of y, that becomes x. So that's the inverse of the relationship. Okay. So if we take this first relationship, 3x plus 5y, if we found the intercepts when x is 0, y would be 3, when y is 0, x is 5. So we have a straight line. Graphically, if we interchange the coordinates x and y, wherever we have the line where x and y are equal, or the 45-degree line, nothing on that line gets interchanged in the inverse, but any other point would be reflected through that 45-degree line. So take a line, invert, switch x and y, we reflect all the points on the one line to the other one. So the inverse is always a reflection through the line x equal y graphically. Now, we will return to a particular type of relationship. So back to equations. So quadratic or second degree equations in two variables, but a particular form where we keep y and then a general second degree polynomial in the other variable. So the shape of these graphically, they're called parabolas. So parabolic shape. Generally cup shape upward, downward. It will have a vertex and a line of symmetry. So a vertex, in this picture, the lowest point, and it could open downward instead of upward and have a highest point, but it has this vertex where it reflects one side is a reflection of the other across the line through the vertex. In this setting, the vertex coordinate x can be found from minus b over 2a. So for example, y equal 2x squared plus 8x minus 5. If we find the vertex, we would have a coordinate of minus 8 over 2 times 2, or in this case, minus 2. The other coordinate of the vertex then is substitute minus 2 back into the equation and compute that coordinate. So we have this point minus 2 minus 21, which is at the center of the parabola, which opens upward around the vertex. So this general shape. And I know it opens upward because coefficient of x squared is positive. Now, I roughly sketched this in. I know it's symmetric about the line of symmetry through the vertex, but to get a slightly better sketch, I might get another point, one of which would be a y-intercept. I could also look for x-intercepts. The y-intercept, if I substitute x equals 0, I end up with a constant term minus 5. X-intercepts, well, y is 0, so I need to solve 0 equal 2x squared plus 8x minus 5. Or x, if I substitute into the quadratic formula, I get minus 4 plus or minus square root of 26 all over 2. So I get those two values. And so the x-intercepts, 4 plus minus 4 plus square root of 26 all over 2. And the other one at minus 4 minus square root of 26 all over 2. And then the y-intercept we have here at minus 5. So, I gathered that information. Maybe my sketch wasn't the best. So, let's start over a little bit. relative to the points, I had the one value minus 21 minus 2 as a point. The other point, it crossed up here at minus 5 for the intercept. And it comes up very thin. And I could graph in these x-intercepts, which are nice, but I could also get, once I get one point on the parabola, other than the vertex, I can move across symmetrically. And produce another point. So if this middle is at minus 2, this was 0, so if I move 2 units the other way, I should get another point on the curve. So this was 0 minus 5, this should be minus 4 minus 5. If I wanted to look at the inverse relationship, that would have been x is equal to two y squared plus 8 8y minus 5. So if I had that one picture, I could reflect through 45 degrees and draw the same picture. Of the inverse. So every point on the red curve reflected across a 45-degree line. So it's the same parabola picture, but just reflected. And then with parabolas, if we knew the coordinates of the vertex, instead of y equal ax squared plus bx plus c in general, this equation becomes essentially just needing to know a. If we take the vertex coordinates and subtract so y minus the y coordinate is equal to ax minus the x coordinate squared. So it takes a much simpler form if we know the vertex. So for example, if we know the vertex of a parabola was 2, 1, and another point happened to be the point 4 minus 2, we would get an equation y minus 1, the coordinate of the vertex, is equal to some coefficient a, and then x minus coordinate of the vertex squared. And so to determine the a, we have the one more point, minus 2 for y, minus 1 is a, and the x coordinate 4 minus 2 squared. And so now a must have been this minus 3 divided by this 2 squared. So from knowing the vertex and one other point, I can reconstruct an equation for the parabola.